Good afternoon. I am from QunaSys. I am Yūya Nakagawa. Thank you very much for giving me the opportunity to talk to such a distinguished audience, and I'd like to thank the organizers and executive members and all the participants today. So my presentation is in technical track, so my presentation will be technical. The title is Algorithm Developments for Quantum Chemistry Calculations of Molecules and Materials with Near-Term Quantum Devices and Early Fault-Tolerant Quantum Computers. More specifically, one experiment and research that I have done more recently will be presented. And what's included in this title is a NISQ device, and I'm sure you're familiar with that. But early fault-tolerant quantum computer is something that I'd like to add more. The fault-tolerant quantum computers, once they are ready, then various complex quantum computing could be made possible, but it is not immediately going to solve all the problems, and we're not able to create the fault-tolerant quantum computers immediately, so it is going to be gradual. So compared to the NISQ device, there will be less error rate. So there's going to be a research that will be focused on early fault-tolerant quantum computers, which is less errors. So that's why I have put this together as a title. And this is based on this experiment, local variational quantum compilation of large-scale Hamiltonian dynamics. And if you do this, go to this URL, then you can see this preprint. And Mr. Mizuta, who was an intern in a company, who is now in the RICAM, and Professor Mitarai and Fuji from Osaka University are collaborating with me. And if you're interested, please take a look. And I'll be talking about this more specifically in this presentation. And since this is a technical track, my talk will be quite technical. But the target of this research is a time evolution operator. And when you say time evolution operator, if Hamiltonian H is given, then minus IHT, E minus IHT, U equals I, E minus IHT. This is the equation. And the quantum circuit will implement this at polynomial cost. So this is one of the fundamental reasons for quantum computing. So you implement this time evolution operator, and this is going to be quite important to do this, to realize the quantum advantage. And the more specific applications include quantum phase estimation on the left. So energy-specific eigensolver, eigen number will be resolved. And if there is a time evolution, what is going to happen? And that is what quantum dynamics is about. And this is from the Google team using a quantum device. And in 1D Harvard model, the charge and the spin, those spread or dispersion is being looked at. So time evolution operator is important, and implementing this on quantum circuit is important. And more specifically, compiling, what we call compiling is what I'm going to use. And on the left, the exponential minus IHT, this operator is used, and this will be replaced by the more visualized quantum circuit. And how are we going to compile this? The two major prior studies are there. One is Suzuki-Toller decomposition. As you can see in the equation, H1 and H2, the local volumes or quantities for Hamiltonian, and if the number of gates is not many, then you can use each of the Hamiltonian, and how you can compile on the quantum circuit is known. And the pros for Suzuki-Toller decomposition is that if the physics is 50 qubit, and as long as you have 50 ancillary qubits, then you can make it work. But the issue is that the delta t should be smaller. So if you need a more preciseness or accuracy, the number of steps will be increased, and ultimately the number of gates or the depths needed will be larger. That is the disadvantage. That is the first one. And the second one is Taylor expansion, qubitization. There's no equation here, but the prior study on the right bottom is the one that is shown. And compared to total decomposition, the pro is that time, if you simulate time t only, how many gates will be necessary if you consider that equation, then compared to total decomposition, the t dependency or scaling is better. But compared to the qubit, there will be many ancillary qubits will be necessary. That because of that, in the NISQ device currently available, in terms of ancillary qubits, it's very difficult to compile this compared to the many more gates required. So these are the prior studies. What is most also important as the previous study that we referenced is a quantum-assisted quantum compiling, QA/QC. And this was featured in the magazine Quantum. And a time evolution operator was approximated by using a variational quantum circuit. And more specifically, what you want to approximate, if there is a U, the V theta, the quantum circuit, which is defined in shape, the variational quantum circuit is used to approximate that. And more specifically, as you can see on the left equation, the two unitary operators or two quantum circuits distance is defined as a cost function, and then the variational quantum circuit parameters will be minimized. And I'm not going to go into details, but the quantum circuit that is on the right bottom can be used for computation. So you calculate the cost function so that the theta will be updated to minimize that. And to give you the algorithm in the quantum computer to the U that is to be compiled, the V theta, the quantum circuit that has the parameters will be evaluated, and you will update the theta so that the cost function will be minimized. And the cost function is more than 0 and less than 1. And if the cost function is 0, then it will be ideal and aligned. So the cost function should be minimized. And if it is closer to 0, then U, the operator, the theta opt, the most appropriate parameter can be used, as you can see in the right-hand side. So qubitization or Taylor development, compared to that function, the ancillary qubits are not required in this. And compared to total decomposition, so you can represent U with a shallower circuits. And that prior example has been already shown in the prior studies. So this is a very good research, but the challenge is that the time evolving operator should be implemented first to approximate that. So you have to consider how you can compile U first, and so you have to assume that first. So we wanted to address this issue and also come up with a good way to compile the variational quantum circuit. And so what we have come up with is local variational quantum compilation, LVQC. And there are so many diagrams here. But what we propose is that if there's a number of if there's a L number of qubits, then QVQC is used to do the compilation. But if the time cube is short enough, then the total L doesn't have to be used. So L tilde, the more local, log L, or you don't depend on L. So in the very small limited area, you do the compilation and computation, and then you can compile the time-evolved operator. So this can be proven universally by Lee-Robinson bound. So this can be broadly applied. So I'm going to talk about this more in the remaining 9 minutes. So now the Lee-Robinson bound. So this is quite mathematical. So you don't have to understand mathematical equation, but a theorem on the limit of speed of correlation spread for a Hamiltonian on a lattice with local interactions. So the left bottom is the equation. It's quite complicated, but what this means is that in the specific site J impact, so the VLR, which is defined, which is the speed, and also this is determined by the size 2VLR t plus psi. So this is a non-relative model. So effectively, if the site is more distant, then there is a finite speed for the transmission. And in any model, of course, it depends on each model, but there is a specific number. And if the speed is more than that, then information will not be communicated. So this is Lee-Robinson bound. So based on that, theoretically, we have guaranteed this. So this is a setup for a study. First, HL. The target Hamiltonian is represented as HL, and there is a Lee-Robinson bound assumed for this, and this is a universal assumption. There is a finite range, a short range, a long range interactions, and you can use various models, and the minimize C something. There's this equation, exponential minus IH, parenthesis LT. So at L size, the variational quantum circuit is, so the cost function should be 0. And V theta is the invariationally or translationally invariant systems. And this will be overlapped between the quantum bits. And based on this setup, this is the main theorem. So left term in blue is the cost function for size L. So if there is a theta opt for size L, there's the VOC, how much it is time evolved is shown. And then you can bound this at the size L, and on the right term, the size L tilde, which is smaller than L, and the cost function for size L tilde, and also contribution from L tilde, which is in green, are included. So if you look at this equation, the green part should be small enough, and that's how you set the L tilde. So L tilde smaller than L, you have to have a general equation, and if you take L tilde Vt plus psi, and then the green will be reduced, and then the blue, the cost function, can be bound by the size L tilde function. So if you compile this with size L tilde, which is smaller, and time evolution should be approximated. And if you derive theta, then if you assign the theta opt, then you can have variational quantum circuit for size L as well. And you can actually show similar equations for other cases. So if L tilde is used to determine the VOC, then you can actually enhance and scale that to size L as well. And this is a proof, and it is quite complicated. And Mr. worked hard to do this proof. So if you're interested, please take a look at this thesis. So I spent 1 night or 2 nights to study this. Once again, advantage of LVQC. What are the advantages of LVQC? So L tilde, compared to the original size, L tilde is not proportionate, and it's only gets larger at log L. So you can determine the quantum circuit at a very small size. So if the large L is 50 qubits, you cannot use classic computers, but L tilde, if this is small enough for classic computers, like 20 qubits or 30 qubits, and you can optimize the variation and then determine theta, and you use NISQ device, FTQC device that can work the 50 qubits, and then that quantum circuit that can be determined, that has been determined, can be used with the NISQ or FTQC. So there is a numerical example, Heisenberg chain, which is often used in NISQ, and the time is 2.5, and the size that was simulated was 40, and compilation size was 20. And this is the experiment that we have done, and the left term is the cost function, and the right one is a super time dynamics. And at 20 qubit, the optimization was done, but at the 40 qubits, which is original size L, compared to Trotter decomposition, there is a circuit that was derived which has enough accuracy. And you fix time t, and theta opt, which is optimized, has been derived. And as for the integer multiple of t, if you run this circuit many times, then for the time that is the multiple of integer of t, you can have a circuit, quantum circuit. And this is the numerical example. And blue is the exact time evolution, and orange is 0.8, 1.6, the time evolution with integer multiple of the time. So in the longer time, you were able to run a certain decent level of simulation. So to sum up, the LVQC was something that we have come up with, and for this one, there is a system L, which is large in size. Lee-Robinson bound, which is universal theorem, is used, and in the short time is short enough, then you don't have to depend on size L, and with a very small size L tilde, you can simulate the time evolution, and at the large size L, you can determine the time evolution operator with a large size L. So in the NISQ era, one of the applications is, as I said, you take the L tilde, which is workable in NISQ device, and simulate this. And if the 50 qubits or 60 qubits may not work in NISQ, but you can actually use NISQ at a smaller L tilde. So you can actually mitigate the issue of having many quantum computers. So we have focused on time evolution, but phase estimation could be another application that we can consider. Thank you.